Everyone knows the universe is vast, but how vast exactly? That simple question has fascinated humans for thousands of years. In ancient China, the philosopher Lao Tzu imagined the universe as something without beginning or end, eternal and boundless. Much later, in the 20th century, modern physics and astronomy painted a different picture. The universe had a starting point, the Big Bang. If the universe began from a single, explosive moment, then just how big has it become since? In this story, we're going to travel outward step by step, from Earth to the Moon, the Sun, the edge of our galaxy, and then to the limits of what we can see, to try to feel, even just a little, how overwhelming its size really is. Starting from home, Earth. Let's start from home, our Earth. At the equator, Earth's diameter is about 12,756 kilometers. If you tried something crazy, walking all the way around the planet, and you walked at about 7 kilometers per hour for 15 hours every day, you'd need around 381 days of continuous walking to complete just one loop. From our human perspective, that feels enormous. But on the scale of the universe, Earth is just a tiny grain of dust. The first step outward, the Moon. Now let's leave Earth. The nearest major celestial body to us is the Moon, at a distance of about 384,400 kilometers, roughly 30 times Earth's diameter. You obviously can't walk there. To reach the Moon, you need a rocket that can at least reach escape velocity, about 7.9 kilometers per second. If, in theory, you could fly in a perfectly straight line at 7.9 kilometers per second the whole way, you'd get to the Moon in about 13.5 hours. In reality, space missions take several days to arrive. But even when you finally stand on the Moon and look back, Earth suddenly looks small, very small. And this is only the first step out into space. Our star, the Sun. Leaving the Moon behind, let's head to the Sun, the only star in our solar system and the source of all the light and warmth that keeps us alive. The average distance from Earth to the Sun is about 150 million kilometers. If you tried to travel there with the same 7.9 kilometers per second rocket, never slowing down, you'd have to fly for roughly 220 days straight. Compared to the size of Earth, this distance is staggering, but even 150 million kilometers is nothing compared to what's waiting farther out. The most distant planet, Neptune. Let's keep going, all the way out to the most distant major planet of the solar system, Neptune. Neptune orbits the Sun at around 4.5 billion kilometers away. Using that same rocket with a speed of 7.9 kilometers per second, you'd have to travel non-stop for over 17 years to get there. By the time you reach Neptune, you might feel exhausted just imagining this journey. Space doesn't just feel big anymore, it feels endless. At this point, we clearly need a faster ship. Upgrading the ship, the speed of light. So let's imagine a futuristic spacecraft. We'll call it our Amazing Explorer, that can fly at the speed of light, approximately 300,000 kilometers per second. At this speed, the trip to Neptune, instead of taking 17 years, would take only about 4 hours. You might think, great, with a ship like this, the universe is basically in our pocket, right? Not at all. We've only just started. The Sun's nearest neighbor, Alpha Centauri. Now let's leave the solar system and visit the nearest star system to the Sun, Alpha Centauri. Even at light speed, to get there you would need to travel for about 4.35 years without stopping. That distance is about 4.15 times 10 to the 13 kilometers, roughly 41.5 trillion kilometers. If we compare that to Earth's diameter, this distance is about 4 billion times larger than Earth itself. At this point, the scale becomes almost impossible to imagine, but Alpha Centauri is still just our next-door neighbor in the galaxy. Our bigger home, the Milky Way galaxy. The Sun is only one among more than 200 billion stars in our galaxy, the Milky Way. The Milky Way is a huge spiral galaxy with a diameter of roughly 120,000 light-years. That means even if you had a spacecraft that could travel at the speed of light, it would still take you 120,000 years to cross from one side of our galaxy to the other. To put that another way, even if your descendants kept flying in the same ship generation after generation for 1,000 generations, they still wouldn't make it all the way across. And remember, this is only one galaxy, our galaxy's neighbor, Andromeda. Now let's look beyond our galaxy. Our nearest large galactic neighbor is the Andromeda Galaxy. The distance from the Milky Way to Andromeda is about 2.5 million light-years. So even at light speed, you'd need to travel continuously for 2.5 million years to get there. If you want to convert that into kilometers, you can multiply 2.5 by about 9.5 trillion kilometers, the distance light travels in 1 year. The resulting number is so huge that it's almost meaningless in everyday life. It's a distance our brains simply aren't built to truly grasp. And yet, when we finally arrive at Andromeda in our imagination, we've still only wandered through a tiny corner of the cosmos. Going farther, the most distant galaxies. Astronomers estimate that the universe may contain hundreds of billions of galaxies similar to the Milky Way. Some of these galaxies are incredibly distant. One notable example is a galaxy in the constellation Ursa Major, designated GN-Z11. In your transcript, it was called Z11. It has a very high redshift of about 11.1, which corresponds to a co-moving distance of roughly 32 billion light-years from Earth. Yes, 32 billion light-years, and even that is not the edge of everything. The observable universe, the bubble we can see. So how big is the universe really? Astronomers define something called the observable universe, the part of the cosmos we can, in principle, see, because light or other signals from those regions has had time to reach us since the Big Bang. Based on current measurements, this observable universe forms a kind of sphere around us with a diameter of about 93 billion light-years. This is what people mean when they say, "Is the universe 93 billion light-years across?" Strictly speaking, that's the size of the observable universe, the part we can detect. Beyond that, we don't know. Our instruments, and even the laws of physics as we can currently test them, simply don't reach that far. A seeming paradox. A 13.8 billion-year-old universe that's 93 billion light-years wide. Here's a question that often confuses people. The age of the universe is about 13.8 billion years, but the observable universe has a diameter of 93 billion light-years. How is that possible if nothing can move faster than light? Isn't that a contradiction? According to Einstein's special relativity, no object made of matter can be accelerated to a speed faster than light through space. But general relativity, Einstein's broader theory of gravity, tells us something surprising. Space itself can expand, and there is no built-in speed limit on how fast this expansion can occur. So, two galaxies can find themselves separating faster than the speed of light, not because they are flying through space that fast, but because the fabric of space between them is stretching. This is why two distant galaxies can recede from each other at an effective speed greater than light, and the observable universe today can be much larger than 13.8 billion light-years in radius, even though the universe is 13.8 billion years old. In other words, we live in a universe where the distance between far-flung regions grows not only because things move, but because space itself is growing. Our limit, what lies beyond 93 billion light-years? Because the speed of light is finite and the universe has a finite age, we're limited to seeing only a portion of it, our observable bubble, about 93 billion light-years. So what lies beyond that? Is the universe finite or infinite? Does it just keep going, full of more galaxies we'll never see? Or does it somehow curve back on itself? The truth is, we don't know. From our vantage point, and with our current tools, both possibilities remain open. When most astronomers say the universe in everyday conversation, they actually mean the observable universe, because that's all we can measure directly. Whatever lies beyond that cosmic horizon remains, for now, pure speculation. Conclusion. So, returning to our original question, how big is the universe? As of now, no one can answer with certainty. What we can say is the observable universe, the part we can, in principle, detect, is about 93 billion light-years diameter. Within it are hundreds of billions of galaxies, each with billions of stars, scattered across an ever-expanding cosmic ocean. Beyond that visible edge may lie even more universe, or something completely unexpected. Part 1. The ISS, where walking means facing death. A spacewalk. It sounds simple, almost like a casual morning exercise, doesn't it? But for astronauts on the International Space Station, ISS, it is one of the most complex and dangerous tasks they ever perform. The ISS is a giant science laboratory orbiting Earth at an altitude of about 400 kilometers, with a mass of roughly 420 tons. The first modules of the station were launched into orbit in 1998, and up to now it has been operating for around 25 years. During that time, the ISS constantly needs maintenance, upgrades, and sometimes urgent repairs on the outside of the station. To support this work, engineers installed a huge robotic arm called Canadarm2, about 18 meters long. Thanks to it, many external tasks can be carried out without astronauts having to go outside themselves. But 18 meters is still not enough. There are areas on the station the robot simply can't reach. And when that happens, there is only one option left. Astronauts must put on their spacesuits, open the hatch, and step out into the void. In a weightless environment, 400 kilometers above Earth, exposed to extreme temperatures and high radiation, a single small mistake can cost you your life. That was exactly the context on July 16, 2013. Part 2. Getting ready for a day at work in space. One morning on the ISS in 2013, astronaut Chris Cassidy, a former U.S. Navy SEAL and an experienced NASA astronaut, woke up as usual. He opened his laptop and began reading the daily reports from Mission Control on the ground. Among them was a report about a technical issue on the outside of the station. It wasn't an immediate emergency, but it needed to be fixed as soon as possible. After discussing it with the rest of the crew on board, Chris decided to wait for a new crew member, Italian astronaut Luca Parmitano, to arrive at the ISS, and the two of them would go outside together to inspect and repair the problem. Luca Parmitano was no rookie. He's an aerospace engineer from the European Space Agency, ESA, a former fighter pilot in the Italian Air Force, with more than 2,000 flight hours on over 40 types of aircraft, and also a highly experienced diver. His flight experience, diving background, and ability to cope with extreme environments quickly earned Chris's trust. From there, they became the pair chosen for this special mission outside the station. Part 3. A fateful step and the first drops of water. 1 week later, on July 16, 2013, after checks and preparation, they climbed into their spacesuits weighing over 100 kilograms, set up pressure, gas, communications, and Chris Cassidy and Luca Parmitano were ready to go outside. The plan for that day: Chris would move along the station's handrails to the data cable area to fix part of an electrical short. Luca would work on the Z1 truss, where pipes and external connectors are located. Everything went perfectly at first. Both of them finished the first tasks 5 minutes faster than the planned 45 minutes. But then, something wasn't right. As he moved on to the next area, Luca felt something strange at the back of his head. It felt like liquid was touching the back of his head inside his helmet. At first, he thought it might just be a minor communication issue, perhaps a bit of water from some internal system. He knew the EVA suit used water to cool the body, but that cooling system is completely sealed, so in theory, water should never appear inside the helmet. But that strange sensation quickly turned to a nightmare. More and more water appeared. It seeped into his ears, affected the microphone, and disrupted his ability to communicate with Chris and Mission Control. Luca realized the situation was serious. He decided to abort the mission and return to the ISS airlock. But as he turned back, the water didn't stop. It continued to rise, flooding his eyes, nose, and mouth. Luca could no longer see anything, and breathing became extremely difficult. In the middle of space, inside a sealed suit, he was drowning. In a moment of near death, what did he do to save himself? How did Chris help his crewmate? Part 4. A silent fight for survival. As an experienced diver, Luca knew how to hold his breath for a few minutes, but this wasn't the bottom of the ocean. This was open space, 400 kilometers above Earth. Panicking, nearly blind, he had no idea where the airlock was. No tear could fall, but inside the helmet, his mind was collapsing. Luca later described the moment. The feeling was terrifying. I was like a blindfolded man forced to move at an altitude of 400 kilometers while water kept filling my mouth, nose, and eyes. I thought I would pass out, and then death would follow. It was only a matter of time. At one point, he even thought about opening his helmet, but he knew that if he did, the pressure difference would make him lose consciousness instantly, and death would come even faster. To drown inside a small helmet in the middle of space, it's a scenario so haunting it's hard to even imagine. But his survival instinct and the calm training of an Air Force officer saved him. In his desperation, Luca suddenly remembered the one thing still connecting him to the station, the safety tether. He began to follow the tether and the handrails along the ISS structure, feeling his way bit by bit as the water kept rising. On the other side, Chris Cassidy realized his crewmate was in trouble. He immediately moved toward Luca to help him. Finally, Luca's hand found the airlock handle. Chris arrived just in time to help pull him inside. Once back in the station, the crew quickly removed his helmet. Water spilled out, and with it, Luca's last hope of survival turned into reality. Thanks to the team's emergency skills and quick reaction, Luca survived. He was conscious, he could breathe, but the experience would haunt him for the rest of his life. Part 5. Investigating the incident and the lesson carved in memory. The 2013 incident is considered one of the scariest events in ISS history. NASA and its partners immediately set up a special investigative board to determine why water from the cooling system had leaked into the helmet. Surprisingly, even after 6 months of investigation, engineers still could not pinpoint the exact root cause of the leak. However, they didn't wait for a perfect explanation to act. NASA quickly implemented improvements to the EVA spacesuits, adding a backup breathing tube inside the helmet, updating procedures, and upgrading safety systems so that if a similar problem occurred, the astronaut would still have a chance to survive. Luca's story became a life-or-death lesson for future generations of astronauts. A spacesuit is not just clothing, it is a miniature spacecraft. It protects you, but if something goes wrong, it can also become a deadly threat. Part 6. 2 types of spacesuits. They're not all the same. You might think, a spacesuit is just a spacesuit, right? In reality, there are 2 main types. Launch and entry suits, worn during launch and re-entry, protect astronauts in case of cabin depressurization, gas leaks, and other emergencies inside the spacecraft. EVA suits for spacewalks. EVA stands for extravehicular activity, activity outside the vehicle. This is the type of suit Luca and Chris were wearing. An EVA suit is essentially a small spacecraft shaped like a human body. It must provide oxygen for breathing, maintain proper pressure, shield the astronaut from vacuum and radiation, regulate body temperature, allow the astronaut to move and work, and support communication with the station and ground control. It all consists of two major parts: the pressure garment, the body-shaped part of the suit, upper torso, lower torso, helmet, gloves, protect the body and allow movement. The life support system, on the back, like a backpack, contains oxygen tanks, fans to circulate air, a system to filter out CO2, a water tank and cooling system to control body temperature, power supply, radio communication equipment. All of this has to work perfectly for hours. Just one small malfunction, like the water leak in Luca's helmet, can push everything to the brink of disaster. Part 7. The Next Generation Suit, Preparing to Return to the Moon. Today, NASA is developing a new generation of spacesuits for the Artemis missions, which aim to return humans to the moon. This new suit design is often referred to as XMU and some commercial variants, and was unveiled in March 2023 in partnership with Axiom Space. Some of its key improvements: greater flexibility, allowing astronauts to move, bend, and twist more easily on the lunar surface; better thermal protection, able to handle the moon's extreme temperature swings better than the Apollo-era suits from more than 50 years ago; multiple layers of protection against lunar dust, radiation, and impacts; Imagine a free camera in the universe that moves at a made-up speed, 1 light-year per second. It ignores real-world limits like relativity, fuel, and acceleration. This isn't about real travel. It's a way to help your brain feel cosmic distances using seconds instead of huge numbers. 1. Solar system, suddenly tiny. 1 light year, approximately 9.46 trillion kilometers. Earth-Sun distance equals 150 million kilometers, a tiny fraction of a light year. At 1 Ly per s, you cross the whole planetary region, Earth, Jupiter, Pluto, Kuiper Belt, etc., in milliseconds, reach the edge of the Sun's particle bubble, Voyager 1's region, in 0.002 seconds. Result: the solar system you thought was huge shrinks into a tiny dot you flick past instantly. 2. Leaving the Sun's territory. The Oort cloud maybe extends to about 1 to 2 light years. You spend only 1 to 2 seconds crossing it. The Sun's Hill sphere, where its gravity dominates over nearby stars, is also about 1 light-year scale. Once you pass that, you've truly left the solar system in a gravitational sense. But compared to the Milky Way, 100,000 light-years across, you've barely moved a pixel. 3. Local bubble and nearby stars. Our solar system sits in the local bubble, a 1,000 light-year wide cavity of hot, thin gas carved out by ancient supernovae. At your speed, you cross it in about 1,000 seconds, about 17 minutes. On the way, you pass Proxima Centauri, about 4 light-years to 4 seconds, Barnard's star, about 6 light-years to 6 seconds, Sirius, about 8.6 light-years to 9 seconds, Vega, about 25 light-years to 25 seconds. The bubble's edges are sites of new star formation, where old explosions compressed gas and triggered new generations of stars. 4. The Milky Way. Disk, bulge, black hole. Milky Way disk about 100,000 light-years across, about 90 seconds at your speed. It has spiral arms, equal density waves or traffic jams, not solid arms, thin disk, young stars, gas, star formation, and thick disk, older stars, puffier, chemical gradients, inner galaxy is richer in heavy elements, which makes it better for building planets, and a warp and dust lanes. It's not a perfect flat disk. At the center, stars orbit at thousands of kilometers per second around Sagittarius A star, a supermassive black hole, about 4 million solar masses. We've tracked stars like S2 to prove its mass. The Event Horizon Telescope imaged its surrounding light ring or shadow. Huge Fermi bubbles above and below the plane show past energetic activity near the core. 5. The halo and dark matter. Leaving the disk, you enter the halo. Globular clusters, ancient dense balls of stars greater than 10 billion years old. Stars and clusters move in ways that can't be explained by visible mass alone. The Milky Way is embedded in a huge dark matter halo, maybe 200,000 to 300,000 light years across, 5 to 10 times more massive than visible matter. Evidence? Flat rotation curve, outer stars orbit too fast, motions of clusters and stellar streams, shredded dwarf galaxies. Conclusion: most of the galaxy's mass is invisible dark matter, shaping everything. 6. Local group to clusters to superclusters. Zoom out further, local group, Milky Way, Andromeda, Triangulum, plus dozens of dwarf galaxies. Milky Way and Andromeda are on a collision course, merge in about 4 to 5 billion years. Bigger still, clusters like Virgo, thousands of galaxies held together by even more dark matter. Between galaxies, super hot X-ray gas with more mass than all the stars. Gravitational lensing, arcs, stretched background galaxies, proves the dark matter distribution. Larger yet, clusters group into superclusters, like Laniakea, our home basin. Galaxies aren't static. They flow along gravity downhill toward large mass concentrations, like the Great Attractor, Shapley, etc. 7. The cosmic web. On hundreds of millions of light-year scales, galaxies trace a cosmic web, filaments, nodes, clusters, and voids. Simulations plus redshift surveys, like the Sloan, show that matter prefers filaments. Voids are underdense and expand a bit faster and push galaxies to filaments. A lot of the missing normal matter is in the warm, hot intergalactic medium, WIM, in filaments, detected via faint absorption features. 8. Looking back in time, galaxies and cosmic noon. Deep fields, like Hubble and JWST, show that even a blank patch of sky is full of galaxies at many redshifts, Z, meaning many cosmic epochs. High Z galaxies, smaller, clumpier, more irregular, with huge star formation rates. Global star formation peaked around Z equals 2, cosmic noon, and has declined since. JWST found surprisingly massive galaxies at very high Z, about 10 plus, nudging us to refine models of how fast structure can form. 9. Before galaxies, dark ages, first stars, and reionization. After the Big Bang, hot plasma turns to recombination, about 380,000 years, neutral hydrogen and the CMB. Dark ages, no stars yet, just dark matter and neutral gas. Population 3 stars form, massive, metal-free, short-lived, forging the first heavy elements. Their UV light and early quasars reionize the universe. Neutral gas becomes ionized again. Future or ongoing 21-centimeter experiments aim to map hydrogen during these eras, giving a movie of the Dark Ages and cosmic dawn. 10. The CMB, oldest light and precision cosmology. The CMB, light released when the universe first became transparent, about 380,000 years ago. Today, a 2.7K black body with tiny temperature ripples, about 10 to the -5. Those ripples are frozen sound waves in the early plasma. Their power spectrum lets us measure curvature, approximately flat, baryon density, dark matter density, dark energy fraction, etc. Polarization and lensing of the CMB give extra constraints on how structure grew and on things like neutrino masses. 11. Inflation, quantum fluctuations to cosmic structure. Problems? Horizon problem, opposite sides of the sky are too similar. Flatness problem, universe is too flat without insane fine-tuning. Inflation, a very early, ultra-rapid expansion, smooths and flattens the universe and stretches quantum fluctuations to cosmic scales. Those fluctuations become the seeds of the CMB ripples, galaxy clustering, the cosmic web. Different inflation models are constrained by CMB spectral index, about 0.96, not exactly 1, fluctuation amplitudes, and limits on primordial gravitational waves, B modes. 12. Hard limits, observable universe, dark energy, and horizons. Observable universe radius approximately 46 billion light-years because space expanded while light was traveling. Outside that, more universe, but we can't see it yet, and dark energy means some regions we never will. Dark energy, likely a cosmological constant, causes accelerated expansion. There's a cosmic event horizon. Some galaxies are so far that any light they emit now will never reach us. In the super far future, only our local group or merged galaxy will remain visible. We know dark energy exists from distant supernovae, CMB, baryon acoustic oscillations, but we don't know what it fundamentally is. Final message of the video: your imaginary speed is just a storytelling trick. The real lesson is about scale, structure, and limits. Space is mostly empty, yet filled with structure on every scale. Most matter is dark, most energy is dark energy. There are hard limits to what we can observe, no matter how advanced we get. Cosmology isn't finished, it's a precision science with big open questions. If you'd like, I can turn this into a shorter script in your style. Profile of the third interstellar visitor. In July 2025, the automated telescopes of the Atlas survey picked up a faint streak slowly drifting against the background of stars. Its orbit was recalculated several times, and the conclusion was crystal clear. It was not following an elliptical go-out-then-come-back orbit like everything else in the solar system. Its orbit was a hyperbolic path, which means it enters the system, sweeps past once, then disappears forever into the space between the stars. That's why it was named 3I/Atlas. 3I, the third confirmed interstellar object, after 1I/Oumuamua and 2I/Borisov. Atlas, the name of the project that discovered it. Archived images were then dug up, and people realized it had been quietly drifting in the data for months already. When astronomers ran the orbit backwards, they saw this. 3I/Atlas is hurtling through the solar system at about 58 kilometers per second relative to the Sun. Its trajectory shows it wasn't born here, but comes from the thick disk of the Milky Way, possibly more than 10 billion years old. In other words, it's an interstellar elder, wandering the galaxy longer than the Sun has existed. 2. 29-10-2025. Perihelion at a harmless distance. By October 29, 2025, 3I/Atlas reached perihelion, its closest point to the Sun. Distance 1.36 AU, between the orbits of Earth and Mars. In other words, it stayed farther from the Sun than Earth is. In simple physics terms, the gravitational pull it exerts on the Sun is tiny, far weaker than that of the planets. Any electromagnetic field it has would be crushed down to almost zero by the inverse square law at that distance. According to all standard models, 3I/Atlas should have been just a normal passing comet. Snap a few pictures, take some spectra, log it in the catalog, and that's it. But it was not normal. 2.1. The first images, familiar yet strange. A whole arsenal of instruments locked onto it. Hubble imaged the coma structure and dust tail. James Webb examined it in infrared, picking out individual chemical lines. The JUICE spacecraft, on its way to Jupiter, even took a quick detour to take a peek. The results? It has a coma, a cloud of gas and dust surrounding the nucleus, just like a comet. It's outgassing very strongly, with a long, faint but distinct dust tail. The spectra show? CO2 is dominant, plus water, methanol, HCN, and a whole series of complex organic molecules. So visually, 3I/Atlas looks like a comet, but its behavior is starting to get problematic. 2.2. Brightening crazier than expected. As a comet approaches the sun, it brightens because its ice sublimes, releasing gas and dust that reflect sunlight. Standard models give us a relatively smooth light curve. 3I/Atlas basically looked at those models and tore them up. Its brightness increased much faster than the predicted light curve. Given the amount of light observed, either its nucleus is much larger than expected, or its structure and composition make it hyper-responsive to sunlight. And then comes the thing that really gives astronomers a headache. 2.3. Light polarized in a backwards way. When light scatters off dust grains, it becomes polarized, and the polarization pattern tells us how big the grains are and what they're like. All comets measured so far show polarization patterns that lie in a familiar range. 3I/Atlas, however, shows strongly negative polarization at viewing angles and wavelengths where it should be positive or close to zero. Multiple independent teams measured this and got the same result, which suggests the dust grains have a very unique structure, very porous, fluffy, or oddly shaped. Or their composition includes a lot of weird organic material that's been processed by the harsh interstellar environment for billions of years. And at the same time, the sun goes wild. Right after 3I/Atlas passed perihelion, a magnetic monster appeared on the sun's surface, an active region designated AR4294, with an area equivalent to several Earths combined, firing off a series of X-class solar storms and coronal mass ejections like a factory with failed brakes. Worse still, AR4294 rotated to face Earth, threatening radio blackouts, GPS disruptions, and power grid issues. While solar physicists were busy staring at the sun, some seismologists started noticing something odd in their data. The number of small to moderate earthquakes ticked up slightly in a short time window. They occurred in multiple regions, not huge quakes, just a weird little cluster. On social media, people were saying, "My house just shook out of nowhere," while scientists looked at the timeline. 3I/Atlas, perihelion, Sun, huge active region flares up. Earth, small quakes become more frequent. 3 events happening almost back to back. Coincidence? Or is there some kind of invisible thread connecting them? 4. Mainstream science? No, the physics doesn't allow it. If you ask NASA, ESA, or any solar physicist, could 3I/Atlas have caused AR4294 or triggered earthquakes? The answer is almost certainly no, and they have solid reasons. 4.1. Gravity, a difference of 16 orders of magnitude. Even if we take a generous upper estimate, 3I/Atlas nucleus is a few kilometers across, with a mass of about 10 to the 14 kilograms, a big comet. Compare that to the sun. The sun's mass is 2 times 10 to the 30 kilograms. At a distance of 1.36 AU, the tidal force that 3I/Atlas could exert on the Sun is so tiny it's indistinguishable from zero. 4.2. Magnetic fields and plasma. Not enough energy. The Sun is a gigantic magnetic generator, creating huge magnetic loops in its super-hot convection zone. Regions like AR4294 are the result of swirling plasma, twisted magnetic fields, magnetic reconnection unleashing enormous energy. For a tiny object 200 million kilometers away to flip the switch on such a region, it would need to bring in an amount of energy or electric current that is completely unrealistic for any comet we know of. 4.3. The 11-year cycle. The Sun was already hot-tempered. On top of that, 2025 falls in the maximum phase of solar cycle 25. This is when sunspots, solar flares, CME events naturally increase. History has recorded many comparable megastorms with no interstellar comet passing by. The Carrington event in 1859, the Halloween storms of 2003. So from the perspective of the professional community, 3I/Atlas and AR4294 are simply two events that happened around the same time, not a cause-effect pair. 5. But the weird things are still there. Even so, there are a few details that make some scientists dissatisfied with just saying coincidence, end of story. 3I/Atlas brightened in a very unique way. Its dust polarizes light like no other comet. Its chemistry is slightly off compared to local comets. All of this is real data, not made-up stuff. A small but cautious group prefers to say, we don't fully understand interstellar comets yet. This is a chance to re-examine our models, instead of throwing it all into the coincidence bin and forgetting it. That's the healthy spirit of science. Not jumping straight to the supernatural, but also not brushing things off too quickly. 6. The fringes. Electric universe, conspiracies, and disguised probes. Outside the mainstream science zone, there are always waves of ideas at the edges. 6.1. The electric universe, when currents rule everything. Some groups in the electric universe camp believe that the solar system is a gigantic electric circuit. The plasma sheet metal called the heliospheric current sheet carries real electric currents, and objects like comets can plug into this circuit. In their version, 3I/Atlas passes through a sensitive region of this current, creating an electrical ripple that travels back toward the Sun, and AR4294 is where that ripple concentrates its energy. The problem is, for this scenario to work, you need electric currents and charges far larger than anything we've actually measured. So mainstream scientists treat it as a fringe hypothesis with no solid evidence yet. 6.2. The heartbeat and the probe hypothesis. Some people analyzed 3I/Atlas's light curve and claimed that there are almost periodic fluctuations, like a heartbeat of light. That spawned the idea, what if this isn't a natural comet, but a disguised probe sending out signals on a fixed cycle? In reality, comets always have wobbly brightness. The nucleus. Do you think you're sitting still right now? In reality, at this very moment, you, I, and the entire Earth are being hurled through the cosmos at 600 kilometers per second, plunging straight toward the maw of a gravitational monster that science calls the Great Attractor. What is dragging us along, and is there any way to escape? Hi, I'm Yoki. Today, we're going to decode the mysteries of the invisible force that's swallowing an entire region of space. Stick around until the end to uncover the stunning discoveries about the Great Attractor, discoveries that could change how we see humanity's true place in the universe. If you love astronomy and cosmic mysteries, don't forget to subscribe to support the channel. Thank you so much. But before we talk about that terrifying destination, we need to understand why this motion is so bizarre it kept scientists awake at night for decades. 1. when the universe betrays its own rules. Imagine you're in a pitch-black room and suddenly you feel yourself sliding along the floor, pulled by an invisible rope. You don't see anyone, you don't hear anything, but the feeling of being dragged is real. That was humanity's situation near the end of the 20th century. To understand how absurd this is, we need to go back to 1929. This was when the great astronomer Edwin Hubble made a discovery that shook our understanding of everything. The universe is expanding. Picture the universe like a raisin loaf arising in a oven. Galaxies are the raisins. As the dough expands, the distance between raisins increases. From the viewpoint of any one raisin, all the others seem to be moving away. This is Hubble's law. By that logic, everything in the universe should be drifting steadily away from everything else in a calm, orderly flow. We shouldn't be moving toward anything massive, except for a few very nearby galaxies bound tightly by local gravity. That was the standard model we trusted for decades, a universe expanding smoothly in all directions. But the universe loves playing hide-and-seek with human arrogance. 2. The first clues: the sky isn't the same in every direction. In the 1970s, astronomers started seeing something strange, a crack in that perfect picture. They were studying the cosmic microwave background, CMB, the oldest light in the universe, the afterglow of the Big Bang. In theory, this background should look the same in all directions, like a uniform sea of radiation at about 2.7 Kelvin. But that's not what the data said. They found that one side of the sky was slightly hotter and the opposite side slightly cooler. The difference was tiny, only a few thousandths of a degree, but its meaning was enormous. This is the Doppler effect in action. You can imagine it with the sound of an ambulance siren. When it's coming toward you, the sound waves get compressed, the pitch goes up. When it moves away, the waves stretch, the pitch drops. Light behaves the same way. If we're moving toward a source of radiation, its light is slightly blue shifted and looks a bit hotter. Behind us, the radiation looks cooler, redder. So this temperature difference in the CMB is undeniable proof. We are moving, and not gently. The data showed that the Milky Way, along with our whole local group, including the Andromeda Galaxy and dozens of satellite galaxies, is rushing through space at about 600 kilometers per second, over 2 million kilometers per hour. Pause for a moment and think about that. At that speed, you could go from Earth to the Moon in under an hour. We are sitting on a gigantic spacecraft called the Milky Way, and that ship is being hijacked by something. This goes against the smooth expansion flow of the universe. According to Hubble's expansion, we should just drift away. To pull against that expansion and drag a whole collection of galaxies that together weigh billions of tons, you need a truly colossal gravitational force. So enormous that scientists at the time could barely imagine it. They called this motion a peculiar velocity, but it wasn't random at all. It had a clear direction. When they plotted the Milky Way's motion on the cosmic map, all the arrows pointed the same way. Something out there, far away, was acting like a giant cosmic vacuum cleaner, sucking everything toward it. The zone of avoidance and a monster behind the curtain. To generate enough gravity to overpower expansion across hundreds of millions of light years, this something would need a mass equivalent to tens of thousands of galaxies combined. It would be one of the largest structures we'd ever discovered, a real cosmic monster. But then came the detail that made astronomers' blood run cold. They pointed some of the world's best telescopes toward the direction we're rushing and saw nothing. You heard that right. We are falling headfirst into what appears to be emptiness, or at least that's what it looked like at first. How can something that massive be invisible? Is our physics wrong, or is some supernatural force playing with us? This huge flow of matter challenged the cosmological models of the time. If matter in the universe were really distributed as smoothly as we thought, structures this gigantic shouldn't exist. The great attractor's existence meant the universe was clumpier, lumpier, and more chaotic than we had assumed. So where was this monster hiding? Why could we see galaxies billions of light years away, but not the thing pulling us from our own cosmic backyard? The answer was hidden in the worst place possible, our vantage point inside the Milky Way. By a cosmic joke, we were given one of the worst viewing angles to observe our biggest gravitational enemy. We were blindfolded, and the blindfold is so beautiful we took thousands of years to realize it was blocking our view. The culprit? Our own home. The zone of avoidance, when your galaxy betrays you. In a dark rural sky, far from city lights, you'll see a glowing band arcing across the heavens, the Milky Way, packed with hundreds of billions of stars, including our sun. It's gorgeous, majestic, poetic, but to astronomers trying to solve the great attractor mystery, that beauty is a curse. The Milky Way is a disc-shaped spiral galaxy, and our solar system lies near the edge of the disk, right in its plane. Imagine you're sitting in the stands of a packed stadium. When you look up, you see open sky. But if you try to see who's standing at the opposite gate on the far side, your view is blocked by thousands of heads. That's our situation. Astronomers call that heavily blocked region the zone of avoidance, not because we're forbidden to go there, but because it's a zone to avoid observationally. It covers about 20% of the sky as seen from Earth. For centuries, this was a complete blind spot. Thick clouds of gas, dust, and dense stellar fields form an opaque fog that absorbs and scatters open light. And fate, like a trolling screenwriter, put the great attractor right behind the densest part of that zone. We were blindfolded, and the blindfold is so beautiful we took thousands of years to realize it was blocking our view. That helplessness persisted until technology allowed us to see with new eyes. Visible light, the kind our eyes detect, is easily blocked by dust, but radio waves and infrared light can slip through much easier, like sound passing through a thin wall. In the late 1970s and early 1980s, astronomers started using radio telescopes to probe the zone of avoidance. One of the major efforts used the Parkes radio telescope in Australia. When they converted the radio data into maps, a terrifying structure started emerging from the darkness. The zone of avoidance wasn't empty at all. It was swarming with galaxies, and at the center of that mysterious pull, they found a hidden beast, the Norma cluster, also known as Abell 3267. This is a huge cluster of galaxies, about 220 million light-years away. It isn't a typical cluster. Abell 3267 is extremely dense and massive, containing thousands of galaxies jammed into a relatively small region. Its mass is so enormous, it actually bends light from galaxies behind it, producing clear gravitational lensing. You can almost feel the excitement of scientists at that moment. We found it, they thought. This must be the great attractor. A giant concentration of mass right in the direction of our motion, hidden behind dust and gas. All the pieces seemed to snap perfectly into place. But the celebration didn't last. Once measurements improved, an uncomfortable truth appeared. Based on our velocity of 600 kilometers per second, the mass of the Norma cluster, huge as it is, was nowhere near enough to account for the gravitational pull required. It could only account for about 1/10 of the gravitational pull required. So where was the other 90% coming from? Imagine you're being dragged by a rope. You follow it and see a strong man pulling. You assume he's responsible, but then you realize his strength explains only a little of the tension. There must be someone or something far bigger in the shadows holding the rest of the rope. So Norma wasn't the final answer, just a forward base of an even larger structure. Laniakea, redefining home. To find the true culprit, scientists had to zoom out even further, beyond individual clusters. We started to realize that galaxies don't float around randomly. Size of the observable universe. the numbers are basically in the right ballpark. Age of universe, approximately 13.8 billion years. Because space has expanded while the light traveled, the radius of the observable universe is about 46 billion light years, so a diameter of around 92 to 93 billion light years. Different groups will quote slightly different values, 45.4 versus 46.5 Gala light-year radius, depending on details of the cosmological parameters. But we're talking differences of less than 1%, not giant revisions. The video also mentions a 2024 result by Halpern and Tomasello that slightly shrinks the radius from 45.66 to 45.34 billion light-years, about 0.7% smaller. That is a real, recent analysis based on better handling of the expansion history. So we might have been off by hundreds of millions of light years? Yes, but only at the 1% level, not in a way that fundamentally changes our picture. Dark matter and dark energy. This part is also mainstream. Rough composition of the universe. About 5% normal matter, about 27% dark matter, and about 68% dark energy. Dark matter is inferred from galaxy rotation curves, galaxy clusters, gravitational lensing, and simulations. Dark energy is inferred from Type 1a supernovae plus CMB plus large-scale structure. It's driving the accelerated expansion of the universe. The video's description of the 1998 supernova discovery and the basic idea of dark energy is accurate. Too many galaxies to count. Also good. A 2016 study led by Christopher Consolis estimated that the observable universe contains on the order of 2 trillion galaxies, about 10 times more than earlier estimates, mostly tiny, faint galaxies we can't yet see directly. So the video's more than 2 trillion galaxies, most are too faint to see, is basically right. JWST and the 2 early galaxies. This is a real tension in modern astronomy, not just YouTube drama. JWST has indeed found very distant galaxies with redshifts around Z approximately 13 to 14, such as JADE's GS Z14O, seen when the universe was only 290 million years old. Some of these objects appear more massive and more evolved than standard models predicted could exist that early. Astronomers really are debating whether early galaxy formation was more efficient, whether dark matter behaved differently, or whether some measurements are being misinterpreted. The vibe JWST is forcing us to tweak our models of early galaxy formation is legit. Inflation, CMB, cosmic web, voids, great walls, all broadly in line with mainstream cosmology. Cosmic inflation, very rapid expansion in the first tiny fraction of a second, smoothing the universe and stretching quantum fluctuations into seeds for galaxies, supported strongly by CMB data. CMB, cosmic microwave background, as Big Bang afterglow from 380,000 years after the Big Bang, carries information about curvature, composition, and early fluctuations. Cosmic web, galaxies and filaments and sheets separated by large voids, voids really do occupy most of the volume of the universe. Huge structures like the Sloan Great Wall are real. Others like the Hercules Corona Borealis Great Wall are claimed but controversial. So the general picture the video paints, cosmic web, voids, superclusters, dark matter scaffolding, is fine. 2. What's speculative, oversold, or probably wrong? The universe is 250 times bigger than the observable universe. This is a popular talking point, but you have to read the friend print. Some analyses of the CMB plus inflation say if the universe has even a tiny amount of curvature, then the total universe must be at least 250 times larger in radius than the observable part. That's a lower bound under specific assumptions, not a measurement of the actual size. We don't know if it's exactly 250, 10,000 times, or truly infinite. So the universe is 250 times bigger? Arrow to more accurate, we know the whole thing is at least hundreds of times bigger than what we can see, and it might be infinite. We don't know. The January 2025 94.2 billion light-year universe and 0.1% precision. The video claims that a team in January 2025 combined JWST plus lensing to measure distances with a 0.1% accuracy across billions of light-years. They found the observable universe's diameter is 94.2 billion light-years instead of 93. This supposedly solves the Hubble tension and shows expansion is more uniform, etc. Double arrow, as of December 2025, there is no widely accepted paper or press release matching this description. Current best estimates of the diameter are still around 93 to 94 billion light-years, depending on the exact cosmological parameters you plug in, but not from a new game-changing 2025 measurement that everyone now accepts. The Hubble tension, the difference between early universe expansion rate and late universe expansion rate measurements, is still an active problem, with many new proposals but no consensus "we fixed it" solution. So that whole last act story about January 2025, we nailed it to 0.1% and solved everything, looks like extrapolation or fiction, not current science. Hercules' Corona Borealis Great Wall, and giant structures. The video treats it as a definitely real 10 billion light-year structure that standard physics can't explain. Reality is more cautious. The Hercules Corona Borealis Great Wall is inferred from a concentration of gamma-ray bursts, but many cosmologists think the data are sparse, selection effects might be huge, and it may not be a single coherent structure in the usual sense. So it's controversial, not a slam dunk, this breaks cosmology result. The universe is infinite, new data prove it is infinite. We're not there. CMB measurements, Planck, etc., say space is very close to flat, which is consistent with an infinite universe, but doesn't prove it. A very large finite universe can look effectively flat over the region we can see. Saying patterns strongly support an infinite universe is too strong. The honest state is data are consistent with either a very large finite universe or infinite. We don't know. Supermassive black holes as impossible. TON 1618 and others are ridiculously massive black holes, and JWST has found billion solar mass black holes in the very early universe. These objects do push models of black hole growth, but they don't literally break physics. People are exploring more massive initial seed black holes, faster growth in dense early environments, or primordial black holes. So real, interesting tension, but not "we know this cannot happen." So what should you actually take from the video? If you strip away the hype, the core realistic takeaways are we can now measure distances across the universe using a beautiful chain of methods, parallax to Cepheids to supernovae to redshift, and JWST is pushing those methods into earlier and earlier cosmic epochs. The observable universe is about 90 plus billion light-years across, but the actual universe is almost certainly vastly bigger, possibly infinite. The universe is mostly dark energy and dark matter, with ordinary matter, the stuff we're made of, as a tiny garnish. JWST is genuinely forcing us to revise our models of how fast galaxies and black holes can form, and how the early universe was structured. Some monsters, huge structures, early big black holes, etc., are real puzzles, but they're being worked into the existing framework, not totally overturning all of cosmology. And philosophically, the video's final emotional message is fair. We're tiny, but we're the part of the universe that can ask, how big is all of this, and how do we know?